Hello everyone, welcome back. This is Mr. Coolvault, and in this video we're going to go through an introduction to the nucleus. So the first thing we need to understand about atoms is that not all atoms are stable. Many atoms are stable, they'll stay together for a long time, but a lot of atoms are not stable, meaning that sometimes they will fall apart. Sometimes the nucleus of an atom is unstable and can't stay together. So the nucleus will then just come apart. This is called being radioactive. So when you hear about radioactive isotopes, what they mean is that the isotope or the atom, this particular atom, does not last long. It will decay and fall apart and become something different. So the nucleus basically degrades or breaks apart. So what keeps the nuclei together normally? So this is where the strong force comes in. And the strong force is the force that holds the nucleus together even though the protons want to repel each other. So we know, and you may have wondered, how is it that the protons, all of them are positive, how do they stay together in such a tight space when they're all positive? We know that opposites attract, but we know that the same charges repel. So why aren't the protons repelling each other? Well, this is because of the strong force. And the strong force is a result of neutrons. So the number of neutrons kind of adds stability and strong force to the nucleus. And so that's what's keeping the protons together. Otherwise, the protons would fly apart away from each other. So it's kind of like this rubber band holding these balls together here. That would be kind of analogous to the strong force. So what happens when you have too many neutrons? So the neutrons do have a stabilizing effect, but you can have too many neutrons. So why do the nuclei come apart? It's because we have too many neutrons. So the strong force won't be strong enough to hold everything together. So it's kind of like a rubber band that is stressed too far. It's going to break, right? So the same thing with the neutrons. You put more neutrons into the nucleus, it's going to break. It's going to fall apart. So what happens when it comes apart? Radiation is released. So radiation is energy. It could be particles too. So particles and energy come flying out of the nucleus at very high speeds. So, so this radiation is energy. You could see here we have energy. So you got some radiation or energy coming out here. You've got a particle coming out. So this is what happens when a radioactive item or atom or isotope falls apart and decays. So radioactivity is these particles being released. That's what we mean by radioactivity. So if something's radioactive, it means it's going to release energy. It's going to release these particles, and those particles and energy can then go out and hit other objects like yourself. So here is a diagram or a chart showing what is called the band of stability or island of stability. So you'll see here this band of stability, this green part here. And what that is showing you is any isotopes or atoms in this area are stable. Anything outside of the band of stability is not going to be stable. So any isotopes out here are going to be more radioactive than the ones inside the band of stability. So this is where you have stable atoms, not a lot of radioactivity. Outside of that band, you're going to see radioactivity. You're going to have isotopes or atoms falling apart and releasing energy, radiation, particles. So one of the things you'll notice here is you have this line. This line here represents a 1-to-1 ratio. So this means you have 1 proton for every neutron. So it's 1-to-1. So you have like 5 and 5, 10 and 10. So this line represents equal numbers of protons and neutrons. So you'll see over here neutrons on the top, proton on the bottom. So you'll see here on the x-axis, this is the number of protons in your nucleus, and here you have the number of neutrons. So what do you notice in the band of stability? So the larger atoms, so here the stable atoms are 1-to-1. So here about 1-to-1. But as you get to larger and larger atoms, notice that the neutron-proton ratio is no longer 1-to-1, right? So here, notice that the number of neutrons being added is greater than the number of protons being added. So you're adding more neutrons than protons when you get to other bigger elements. And so this is what I was saying earlier, is like how neutrons have a stabilizing effect. So more neutrons is needed to stabilize the nucleus because you're adding more and more protons. Remember, protons have positive charge. So the more protons you put in the nucleus, the more repelling force there is. So you need a stronger, greater nuclear force, strong force, to hold it together. So that's where the more neutrons come in, right? And so the proton ratio is larger than the neutron-proton ratio is larger than 1-to-1, which is more likely to be unstable and radioactive. So if you get too many, you'll be more unstable. So here, if you're in this band, you're going to be stable. All right, so let's talk about nuclear symbols. So your nuclear symbol, when you're writing the symbol for an isotope or atom, the way we normally write it is you have the element symbol here, just like you normally would. And then you have 2 numbers on the left-hand side. So at the top left is your mass number, and the bottom left is your atomic number. So the atomic number is going to be less because that's only the number of protons. The mass number is going to be greater because that's the protons and the neutrons. So remember, to find the number of neutrons, you have to subtract the atomic number from the mass number. That'll give you the number of neutrons. So let's talk about chemical versus nuclear reactions. So chemical versus nuclear. So chemical reactions occur when bonds are broken. So you're actually breaking bonds between atoms. With nuclear reactions, those are going to occur when the nuclei emit particles and or rays of radiation, rays of energy. So with chemical reactions, you're breaking bonds between atoms. But in nuclear reactions, you're actually looking at a single atom and what's happening at the nucleus when that nucleus breaks apart, so that when it's going to emit particles and or rays of energy. Also, chemical reactions occur are when atoms remain unchanged, although you rearrange them. So in a chemical reaction, you're breaking apart atoms and rearranging and forming new compounds. With nuclear reactions, the atoms themselves are changed into different atoms. So the nucleus is being changed with nuclear reactions. Chemical reactions, the atoms aren't changing, they're being rearranged. Nuclear reactions, the atoms are changing from one element to another. Chemical reactions also involve only valence electrons. So we're only looking at the outer valence electrons. So valence electrons are the electrons on the outside, the outermost part of the atom. We'll talk more about valence electrons later, but it has to do with those outer shell, outer electrons, ones that are farthest away from the nucleus. Nuclear reactions may involve protons, neutrons, and electrons. So it involves all three. Chemical reactions are associated with small energy changes. So you could have what is called, relatively large changes, but compared to a nuclear reaction, they're pretty much small changes in the reaction. Whereas nuclear reactions are associated with very, very large energy changes compared to chemical reactions. So this is where your E equals mc squared comes from, right? So the energy equals the mass multiplied by the speed of light squared, and the speed of light is a very large number, but we won't get into that. And so chemical reactions, for chemical reactions, the reaction rate is influenced by certain outside factors. For example, the reaction rate is influenced by temperature. It's influenced by the size of the particles. It's influenced by the concentration, how many particles I have in a given space, and other things. A nuclear reaction, for the rate of the reaction, it's not influenced by those things. So it's not influenced by temperature, particle size, concentration, etc. So that's another difference between chemical and nuclear reactions. All right, so let's talk more about nuclear reactions here. So isotopes of one element are changed into isotopes of another element. So for nuclear reactions, you're changing the element. Chemical reactions, you're not changing elements. So in order to change an element, we said that the identity of an element is dependent upon the nucleus. So if your isotopes are changing from one element to another, then that means the nucleus is changing. So something in the nucleus is changing, and that's protons, right? So protons can change. So large amounts of energy is released. Talked about that. So when you change the nucleus, large amounts of energy is released, and we use that in nuclear power plants as well, nuclear bombs as well. All right, what are the uses of nuclear reactions? Well, if you can't control the reaction, right, uncontrolled nuclear reactions are very dangerous. That's a nuclear bomb, a nuclear explosion. So when you get an uncontrolled reaction, you get an explosion. But when we use the nuclear reactions properly, they are very useful, and we'll talk about that. So, for example, power plants. You control the reaction in a power plant that produces lots and lots of energy, and we get lots of electricity. That is a power plant. Nuclear power plants are the most efficient way to get electricity. It's the cheapest way to get electricity if we can build more of them. But there's so many regulations these days that it's hard to do. But we should definitely think more about nuclear power. Tracking chemical reactions and biological processes. So one of the things you could do is you could put in your body, which is a tracer called a tracer molecule, and it has a radioactive element in the molecule. Iodine is often used for that sort of thing. You can ingest iodine, and they can use it to look at your thyroid for any problems. So using chemical tracers that have a radioactive isotope in it is very useful for medicine. Radiation therapy for cancer, right? So you could use radioactive isotopes to fight against cancerous cells to destroy those. And you could also use isotopes to find the ages of dead plants and animals, or even rocks, right? This is called radioactive dating. You can use carbon-14. Carbon-14 is a radioactive carbon isotope, and you can use that to date the age of living, or I should say, organic substances that have died or have been used, like paper. And then you have uranium. You can date rocks with uranium isotopes, radioactive isotopes. So let's talk about nuclear fission. Nuclear fission is the splitting of the nucleus. So fission is the splitting, where nuclear means nucleus, so we're splitting the nucleus. This will then cause a chain reaction. So if the nucleus splits, it'll split into different parts. It will release particles from the nucleus, and one of those particles, usually a neutron or several neutrons, will be released from the nucleus, and then those neutrons will then bombard surrounding atoms. Though that will then cause those surrounding atoms to then break apart, releasing more neutrons. And so this will keep happening. And this is what we call a chain reaction. It'll just keep going and going until the whole substance has been split apart. So this will happen in nuclear power plants. It'll happen in atomic bombs, nuclear bombs, and nuclear reactors. So a nuclear reactor is where we control this chain reaction to make sure that energy is released slowly, that we're not letting it go. So nuclear reactors are very important, and so that's where we can control the reaction. So we'll definitely talk more about nuclear reactors a little later. And so this is an example of nuclear fission with a chain reaction. So here you have uranium 235, and here's a neutron. So this neutron is then going to hit the uranium. So the uranium will absorb the neutron, and that's going to make the nucleus bigger. And what we said about big nuclei are unstable. So when this uranium absorbs the neutron, it's going to become unstable and it's going to break apart into two parts. And then in the process, it releases 3 other neutrons. Those 3 neutrons then go out and hit surrounding atoms. So this atom of uranium 238 gets hit. This uranium is 235 gets hit. And so then this uranium is going to break apart, become unstable, break apart. It's going to release neutrons. And then these 2 uranium 235s absorb these 2 neutrons, and so on. And the chain reaction keeps going until you run out of material to undergo fission. So you don't need to write this down. So nuclear fission, the first controlled nuclear reaction in December 1942. That was the first controlled nuclear reaction. And the first uncontrolled nuclear explosion occurred July 1945. I'm sure you can remember that date, July 1945. And the examples of this is the atomic bomb and current nuclear power plants, so controlled and uncontrolled. These are good examples. What about fusion? Nuclear fusion is the opposite of nuclear fission. So instead of splitting apart the atom, you're putting it together. So you're combining nuclei. So this doesn't normally happen because, positives repel each other. 2 positives repel each other. So you have a positive nucleus. You have another positive nucleus. You're trying to put those together. That's hard to do. It doesn't normally happen. So there are pros to nuclear fusion. One, it's inexpensive and there's no radioactive waste. So if we could have a nuclear fusion power plant, that would be a good thing. Plus, nuclear fusion releases a lot more energy, about 10,000 times more energy than a nuclear power plant that runs on fission. There are some cons to it. This is hard to control. That's one con. And there's a large startup energy to get it to go. So those are a couple of things we have to overcome. So examples of fusion reactions: stars, the sun. Our sun is undergoing fusion all the time. That's the main power of the sun is fusion. Hydrogen bombs. There are nuclear weapons called hydrogen bombs that are fusion. They're very powerful. Future nuclear power plants. Hopefully, in the future, we can have a power plant that runs on fusion, and that would be a game changer for the energy industry because we would be able to supply a lot more energy for people and their homes and electricity for people. So, nuclear stability. So, when we're looking at the nuclear stability, there's very stable. So, you have this 6 protons, 6 neutrons, where you saw that 1-to-1 ratio, that's stable. Marginally stable, you kind of see you have about 120 neutrons to 80 protons. So if you're in the atomic numbers, if you're in the range of numbers 1 to 20, you're in the stable, very stable range where the numbers equaled 1-to-1. So ratio is 1-to-1 for protons to neutrons. So an example would be carbon-12. Carbon-12 has a 1-to-1 ratio for protons to neutrons. So marginally stable, you're in the range of 21 to 82. So if you have an atomic number 21 to 82, that is going to be marginally stable. And here you have a ratio of about 1 proton for every 1.5 neutrons. So you need more neutrons than protons to keep it stable. So an example would be mercury 200. And unstable radioactive elements are beyond 82. So any element beyond 82 on the periodic table is going to be unreactive and radioactive. So here you have the ratio is above, it's greater than 1 to 1.5. So that proton to neutron ratio. So you're going to have more protons than neutrons. And so uranium and plutonium are examples of this. All right, let's talk about types of decay. So really quickly, we have alpha decay. So different elements will undergo different types of decay. Alpha decay is where the nucleus emits a particle made up of 2 protons and 2 neutrons. This is like a helium nucleus. So basically, it's the helium atom, but no electrons. So it's not a helium atom, it's just the nucleus of the helium atom. So this is the formula for a nuclear reaction. We'll talk more about nuclear reactions later and how to balance them, but I'm just showing you what it looks like. So here you have the parent nucleus. So the uranium-238, remember the mass numbers on top, the atomic numbers on the bottom. So uranium is going to break down into thorium, and it releases an alpha particle, which is a helium nucleus. And so here's the table. Oops. So the table, alpha radiation, the composition of the alpha particle is helium nuclei. The symbol, this is a little messed up. These 4 and 2 should be down here. So this is the mass number. This is the atomic number. So it should be here. That would be the symbol, He with 4 and 2 here. Or you just got this Greek symbol alpha, and the charge is a +2. And because it's got 4 protons, it's got 2 protons, 2 neutrons, it's going to have mass number of 4. And remember, AMU is just a unit that we use for very, very small objects, very small atoms, particles, and this is atomic mass unit. And then shielding. So you can block alpha particles with paper. So basically, paper is enough to block the particle. And this is the approximate energy of the particle. And then you have penetrating power. It's got low penetration. Because of the low penetration, it can basically be blocked by paper. Next one is beta decay. So for beta decay, you have, instead of an alpha particle being released or a helium atom, you have an element that's breaking down into another element, and it's basically releasing an electron. So an electron is released from the nucleus. That is right. An electron is released from the nucleus. We said that before, that electrons are outside the nucleus, but something happens when particles break down, you can produce an electron from the nucleus. So this here is called the beta particle. it's basically an electron released from the nucleus. That's what we call beta particle. So a neutron in the nucleus is split into a proton and what is called a beta particle, which is like an electron. So it's a negative particle, like an electron. So that is what happens. So a neutron breaks apart into a proton and basically an electron. So think about that. So neutrons seem to be made up of protons and electrons together. So this is the table for beta radiation. So basically the composition of a beta particle, it's the same as an electron. Here's the symbol. You could either use an E negative or beta symbol. It's got a charge of -1 because it's like an electron. This is the size and mass. Like an electron, it's very, very small compared to protons and neutrons. To shield it, you can block it with aluminum foil. So paper will block helium nuclei, the alpha particle, but aluminum foil will block the beta radiation. And so here's the energy for the beta particle, and it's got moderate penetrating power. So it's got more penetrating power. So it can penetrate into 4 millimeters of body tissue. So you need something like aluminum to block it rather than paper. The next one is called positron emission. So positron emission is where you have an element, and that element breaks apart into another element. So the nucleus breaks apart. You get a different element, and out comes a positive electron. So a positron is a positive electron. So in this case, a proton splits into a neutron and a proton. So here you have a proton, it breaks apart, and what you're left with is a neutron and a positron. So like a beta particle, which is that negative particle that looks like an electron, it's basically the same, but instead of having a negative charge, it has a positive charge. So think of it as a positive electron. Next is gamma emission. So gamma emission is where you have an element like uranium-238, and basically it releases energy. So gamma emission is energy. It's not a particle. It has no mass. You can think of gamma radiation as light. Light doesn't have mass. We don't think of it as particles, but in some way we do. We'll talk more later about that. But gamma radiation is where you have your uranium, for example, breaks apart into another element, plus here you have your alpha particle. So recognize that alpha particle. And here, this is energy. So this is related to gamma. So you have this gamma symbol with 0, 0 on top. So 0 charge, 0 mass. So it's just it's basically energy being released. So high energy photons. So photon is basically a particle of light. It's energy. There's no loss of particles from the nucleus. So when you undergo gamma emission, the nucleus mass doesn't change. It just releases energy. So usually after a nucleus undergoes some other type of decay, like alpha decay here, so we have alpha decay here, then you'll also release energy or gamma particles along with that. And then what happens there is that the remaining particles rearrange. So you lose some particles, the remaining particles kind of rearrange, and that rearrangement causes gamma radiation to be released. So here's the table for gamma radiation. So here you have high energy radiation. The symbol is gamma. There's no charge. There's no mass. And shielding requires lead or concrete. So the penetration is very, very high for this. So that's why you need a lot of shielding. And that's the end of the video. Thanks for joining me. If you like this video, please like, share, subscribe, hit